Suppose there is a disease that affects 1% of the population. And we also have a medical test for the disease. And the way it works is if a person has the disease, then the test is positive with probability 95%. And if a person does not have the disease, the test is positive with probability 2%, right? And so this is a false positive. The chances that it'll give you a positive even though you shouldn't, right? So now here's the question. If a random person tests positive, what is the probability that they actually have the disease? And for many people at first, it may be tempting to think of this as, oh, like 95% seems like it's very good, right? So this probability is probably high, but it's a little bit more complicated than that. And the reason is that this number is very important. So the prevalence of the disease in the population is actually going to be a very important thing because intuitively the idea is that if the disease is very low in the population, even though the chance of a false positive might be low, this disease is so low that it's more likely that you get false positives and so on. So actually this number is quite important. And the way to actually deal with this type of questions is something called Bayes' theorem, right? So what does Bayes' theorem say? So Bayes' theorem is quite important. It tells you how you should update your probability when you learn something new. So what's the probability of A given that I learned some new fact B? Well, it's going to be the probability of B given A times the probability of A divided by the probability of B. So let's write the example we are looking at. So if we let A be the event person has the disease, and we let B be the event test is positive, then the idea is that we are interested in, well, what's the probability that someone has the disease given that they tested positive? And what Bayes' theorem tells you is you can find that, and it's going to be related to what's the probability that someone tests positive when they have the disease times the probability that someone has the disease, and then divided by the probability that someone tests positive. And we're going to talk about this division here. This is actually just a normalization factor. It's something that makes this be 1. Essentially what happens is that this is proportional to these two terms on top. And so the idea here is that for the probability of the person having the disease, given the test is positive, to go up, it actually is determined by these two facts. So this probability of B given A is exactly this here. What's the probability that someone has that someone tests positive if they have the disease? This 95% would enter here. So it's making this number go up. But look at this term here. This is the probability that a person has the disease, and that's this 1% here. So the effect of this 95% can sort of be countered by this number over here. Now, if this was higher, of course, it would help out here for this probability to be high. But if this is very low, it can throw this probability lower than maybe one would expect. So let's see how to compute this. Well, from the problem, we have these two. And like I said, we need to deal with this term over here. And the usual way of dealing with this term is using what's called the law of total probability. So what is the law of total probability? So the law of total probability says that if you can partition the whole sample space into mutually exclusive events, right? So these events are all mutually exclusive. It's only one or the other exclusive. Then you can write your probability of an event B as what's the probability of B given event A1 times the probability that A1 will happen plus the same for A2 and so on. And let's focus for now in the simplest case of this, which is when you partition your space into exactly two parts. So if you have your your space omega here, you can partition it into disjoint A and A complement. So remember, A is an event, and then A complement is the event not happening. And the event either happens or it doesn't, and that's why you get this. And also, it cannot be that an event happens and it doesn't happen. So this needs to be the empty set. So this is a nice partitioning of this space. And if we apply this theorem to this here, it says that the probability of any event B is going to be the probability of B given A by the probability that A happened, plus the probability of B given that A didn't happen by the probability that it didn't happen, right? So it's sort of like separating B happening into the two cases, the case where A happens and the case where A doesn't happen. And so with this, we're able to compute the denominator here, and that's everything we need to essentially solve this problem here. So if we go back to our medical testing problem, so if we let again A be the event that the person has the disease, so person has the disease, and B be the event that the person tests positive. So what do we want? Or let's start by what we have. So our problem says that the probability that someone has the disease is 1%. So this is 0.01. And the problem also tells us that the probability that the person, tests positive if they have the disease is equal to 95%. So this is 0.95. And the last thing that we were given was that in the case where the person doesn't have the disease, so the probability that the person tests positive if they don't have the disease was equal to 2%, right? So this was exactly this problem here. So these numbers, this 1%, 95, and 2%, they translate to these probabilities here. And so once again, what are we interested in? We are interested in the probability that the person has the disease given that they tested positive. Well, by Bayes' theorem, this is going to be the probability that they test positive given that they have the disease times the probability that they have the disease divided by the probability that they test positive. And here, let's write it down here, the probability that they test positive, we can rewrite this using the rule of total probability as the probability that they test positive given that they have the disease times the probability that they have the disease plus the probability that they test positive given that they do not have the disease times the probability that they do not have the disease. We have all the values, so this is going to be 0.95 times 0.01, and then plus this one is 0.02 times, and this one here, so if A is 1%, then complement of A is 99%, right? So this will be times 0.99, and if you compute that here, so let's see, if you compute that, you get 0.0293 around, right? And so now we can replace here also. So the probability of B given A, 0.95 times probability of A, 0.01. And you divide this by 0.0293. And this is going to be approximately 0.324. So around 32%. So you see, even though that probability was 95% for the test, so the probability that the person actually has the disease, given that they tested positive, is around 32%. And this may feel a bit surprisingly low, but like we said, the reason is the low base rate for the disease. So this number here is essentially what's bringing it down, right? So the low base rate of the disease, so since the disease is rare, most people do not have it. So among all positive tests, there's actually going to be a significant number that are going to come from false positives, right?